Um, Hello everyone, my name is Chen Mengmeng and I come from Suzhou University in China. It's my honor to have the opportunity of making this presentation. And, uh, and because some reasons, the authors of this paper can't arrive here, so I'm here on behalf of them to report for you. And today my topic is anti-magnetic disturbance, the pedestrian navigation system based on MEMS inertial sensors. Next, I will introduce my topic from the following aspects. Firstly, the background of inertial navigation system, short for INS. And secondly, it's a system overview. And then the pedestrian constraint condition and comprehensive navigation error correction will be introduced in detail. And finally, there are some experiment results. As we all know, there are many disadvantages of global navigation satellite system, short for GNSS, such as high power consumption, signal blocked or reflected, and lost position. Compared with GNSS, INS is low power consumption, self-independent, and suitable for all environments. And there are many scholars who have already conducted a study on fault-mounted INS. The first scholar have proposed the zero-velocity detection method, which set the pedestrian's velocity to zero at static phase. And based on this method, the second scholar proposed that we can regard zero velocity at static phase as measurement of common filter to compensate errors of velocity and attitude. And based on these two methods, the third scholar proposed that we can calculate roll and pitch using accelerator and bend attitude with zero velocity as measurement of common filter. However, there still exists a problem. The zero velocity update short for zero PT could only surprise divergence in a short time due to the weak observation of yaw angle, and the error caused by yaw angle can't be corrected. So we proposed a solution called the comprehensive navigation error correction, short for CNEC. It consists of three parts. First, calculate the observation of heading angle by magnetic field. The magnetic field interference detection is carried out first, and if the magnetic field is disturbed, calculate the reference yaw angle by this trajectory detection. And then regard position drift in static phase as measurement of position error. Finally, correct both the position and orientation error by integrating not only observations of errors in velocity and attitude, but also that of position drift in one common filter and amend them simultaneously. This is a block diagram of our pedestrian navigation system. It consists of 6 parts. Okay. Inertial navigation algorithm and zero velocity detection, zero flight detection, magnetic disturbance detection and minimization, jet trajectory heading detection, and comprehensive navigation error correction. Firstly, we talk about the zero velocity detection unit. It's used to determine static phase of human walking so that the observation and state of current and future can be updated at this moment. And we do zero velocity detection by integrating three methods: the magnitude of sensed acceleration, the magnitude of sensed angular rate, and the variance of sensed acceleration in a given window. And this is the first three figures. And the first three figures is as a result of acceleration variation, accelerate variation, and acceleration variance respectively. And the last figure is zero velocity detection results. Combines these three methods. And from the zero velocity detection results, we found that there still exists a position drift between the two adjacent zero velocity points, and the integration of position drift error can be a non-negligible error. In order to solve this problem, we need some other steps, and we will choose the method next later. This is magnetic disturbance detection and manipulation unit. The magnetic disturbance detection consists body-phase disturbance and external disturbance. This is the body-phase disturbance, and below it is a mirrored distribution of magnetic fields in the body frame when rotation is conducted and the body-phase disturbance is involved. And this two figure is magnetic field strength disturbance detection results and inner product magnetic disturbance detection results. We can say that there are always some points can't be detected by any single method. So we combine these two methods, and the result is shown in this figure. It's obvious that almost all the disturbed points can be detected. A straight trajectory detection unit is used to provide more accurate reference your angle when trajectory is straight, and the mirror when trajectory is straight and the mirrored magnetic field is disturbed. The right figure shows the trajectory of the UPT, and the left figure shows. In the left figure, the red line is ideal yaw, and the blue line is the yaw without straight trajectory detection. And this orange line is the result with a straight trajectory detection. It's obvious that the orange line is closer to the ideal value compared with this blue line. And in the last unit, both the velocity error and attitude error are corrected with a common filter according to its observation input. It's vital to choose the appropriate observation for common filter. To reduce the position drift we mentioned above, we integrated not only observations of errors in attitude and velocity, but also that of position drift in one common feature and amend them simultaneously. And when the detected zero velocity points isn't in static phase, we integrate only the observations of error in velocity and attitude. And this is a hardware system we designed. It consists of three parts: inertial measurement unit, navigation computer, and a human-computer interaction. And this is the indoor test environment. The inertial measurement unit is based on shoes. And there are magnetic field disturbance. From the right figure, we can see that the result of ZUPT and max ZUPT, this circle and this circle, they all deviate from the rectangle shape gradually, and particularly such as the black circle, that it suffers from the magnetic disturbance. This and this circle in this building, and the in comparison, the Shengyuan method, it's the blue line circle. The Shengyuan method does better in bounding the time accumulated error in young angle and overcoming the magnetic disturbance. Generally, the Shengyuan method achieves about 1.84 meter absolute navigation error after 180 meter indoor traveling. That's all. Thank you. Thank you for your attention.